Okay, so this is Chapter 2, Trigonometry, Math 108, Chapter 2. We're going to talk about trigonometric functions of real functions. So this will be Lecture 2. Trigonometric functions of real functions. Okay, and so what's meant by this, basically what the objective of this chapter is, we're going to identify what trigonometric functions are, and it's just another class of functions in as much as that we dealt with algebraic functions from Chapter 1. Now this other class of functions, trigonometric functions, and essentially they're functions that you input a real number and you get out a real number for now, and later on we'll extend the concepts of trigonometric functions where you could potentially put in a real number and get a complex number out, but that'll be later, see around Chapter 5 or Chapter 6. Okay, so here we go. We're going to start off with the unit circle. Okay, interestingly enough. So, as you know, the unit circle is expressed as x squared plus y squared is equal to 1. So this is the equation of the unit circle centered at the origin. So let me see if I can pull up a graph. All right, so we'll go to our graphing calculator utility. And we'll first start off by plotting the graph of the unit circle. All right, so that would be x squared plus y squared is equal to 1. All right, and so the red graph is the sketch of that graph. Now, so here's how we're going to work it for now. I'm going to say let's let the letter t denote a real number. So, and here's how I'll write that. So we say let t, lowercase t, be an element of the real numbers. Okay, so as I explained in last class, this epsilon means is an element of, and this symbol r with a double backbone, that's called the set of real numbers. So t is an element of the real number. Now, if I say let's let t be a real number greater than 0, right? We'll start out that way. And so what I'm going to do is I'm going to define what a terminal point is. Okay, so definition, terminal point. And I'll, instead of writing out a definition, I'll show you graphically what a terminal point is. So if t is greater than 0, suppose t is, say, 2 or 3, or some number, pick a number. And so, like, if I say t is equal to 2.5, if I were to start, say, at the origin on the x-axis, okay, and I walk 2.5 units this way. So I go 2.5, and I stop here. So in this case, we would say t is 2.5. All right, now, so you have a distance from 0 to 2.5, and you see it's denoted by this green line. Now, what if I were to take 2.5 units along the x-axis, and I were to traverse the same distance along the perimeter of the circle? In other words, I walk along the circle an equivalent distance of 2.5 units, as the same distance as shown in the green bar. Where would I stop? Okay, And the point at which I stop would be called the terminal point. Okay, so if I want to traverse 2.5 units, for instance, along the perimeter of the red circle, and I stop, the coordinates of that point would be, or the point itself rather, would be the terminal point, and we're interested in finding the coordinates of that point. All right, so you basically take this linear distance and you fold it onto this circular perimeter, and the point at which you stop would be the terminal point. All right, so for instance, so it could conceivably be something like this. I don't know for sure. We'll have to have a means of calculating it, but so I'm going to walk along the perimeter of the circle 2.5 linear units, but I'm going to stay on the circle, so it kind of bends along the perimeter of the circle. Now, and so we stop at this point, and the abscissa of the point we'll call x, and the ordinate we'll call y. All right, and so P is a terminal point. Now, if t is greater than 0, the terminal point is determined by traversing along the perimeter of the circle in the counterclockwise direction. Okay, so if we progress in this direction, the way the arrow is pointing, this is counterclockwise, which I'll write as CCW, counterclockwise, and t is greater than 0. Right, so the terminal point is found by traversing counterclockwise for cases where t is greater than 0. Okay, all right. Now, if t were less than 0, I would traverse the perimeter of the circle in a clockwise direction. All right, so let's say t is negative 1.5. So suppose t is equal to negative 1.5. So on the x-axis, a linear distance of negative 1.5 would be like this, drawn like this. Okay, so that distance is 1.5. Now, we take essentially this linear distance and we'll fold it onto the red circle, but since t is less than 0, we'll advance clockwise. Okay, by clockwise we mean the direction in which the hands on the clock move. So it could be something like this. I don't know for sure, but we'll find out. All right, and so Q, X, Y, okay, this is the terminal point. Q is the terminal point for t equals negative 1.5. All right. Okay, so now, okay, so we traverse clockwise. Okay, because t is less than 0. All right. Okay. Now, so if I were to take one lap around the circle, walk one lap around the circle, I would have traveled 360 degrees. Okay, so 360 degrees, one lap around the unit circle. Now there's a relation, and you've probably seen this on your calculator. There's a relation between what's called distance along the perimeter of the unit circle is usually measured in a unit called radians, right? And so if I were to say run one lap around the circle for 180 degrees, I'll stop, say at -1 right here. All right, so this denotes 180 degrees, but we can convert the degree measurement into a distance measurement, and that's called radians. Okay, so radians translates into the actual displacement along the perimeter of a circle, right? So if I advance 180 degrees along the perimeter of the circle, okay, in other words, halfway through the perimeter of the circle, I will have traversed pi radians, okay, because the circumference of the circle is 2 pi radians, 2 pi radians. 2 pi r. Remember the formula for the circumference of a circle? Okay, so circumference is equal to 2 pi times the radius, 2 pi r. And that's the measure of the length of the circle, right? And in this case, since r is 1, okay, our r is 1, that's just equal to 2 pi for the unit circle. Okay, this is the unit circle centered at the origin. So so 360 degrees then essentially equals to 2 pi radians. And I'll abbreviate the word radians with the letters rad, R-A-D. So R-A-D stands for radians. So doing the division, you'll have pi radians is equal to 180 degrees. All right, so this is a formula that you'll have to memorize. So memorize this, very important formula. All right, pi radians equals 180 degrees. So pi halves radians, pi over 2 radians, is 1/2 the distance, is 1/2 of this distance. All right, so this would be pi radians. Okay, and let's see, this would be, if I start at the point 1, 10, and I go negative pi radians, then I would go clockwise this way. All right, so this is negative pi radians. Okay, see how that works? Okay, now if I were to go to this point, for instance, say if I want to stop at this point right here, at the point 0, -1. Okay, my t value would be pi radians plus another pi halves radians. So in this case, t is equal to 3 pi over 2 radians. Three pi over 2 rads. All right, so take this down, and I'll do another example. So let me erase this. Now, pi halves radians would be essentially 90 degrees. And you can easily identify 90 degrees on the unit circle. So this would be, okay, so the terminal point, 0, 1, okay, that's equal to pi halves radians, okay, which is equal to t. So t is equal to pi halves radians, and so the terminal point, p, is 0, 1. So if I ask you what is the terminal point for pi halves, you'll answer 0, 1. Okay? If I ask you what is the terminal point for negative pi halves, you'll start at the point 1, 0, and you'll walk along the unit circle for negative pi halves radians, and you'll end up here at point Q, which is 0, -1. All right? So this is for t equals to negative pi halves, which, okay, also equals to the terminal point for 3 pi over 2 radians. Okay? Because we can get to 0, -1 in 2 different ways by going in 2 different directions. So this also equals to 3 pi over 2. Okay, so the terminal point for 3 pi over 2 is the same as the terminal point for negative pi over 2. Right? And likewise, the terminal point for negative 3 pi over 2. Okay, so let's see what the terminal point for negative 3 pi over 2 is. So if I start at the point 1, 0. You always start at the point 1, 0. Basically, this is considered the origin for the unit circle. And I go negative pi halves, negative pi, and then finally negative 3 pi over 2. And so the terminal point for t equals to negative 3 pi over 2, okay, is p, right? So pi over 2 and negative 3 pi over 2 have the same terminal point. All right, so let's do a couple of examples, more examples, some questions then. How about we find terminal points for, say, t is equal to 3 times pi, 3 pi, right? So to find the, now when I ask to find the terminal points for t equals to 3 pi, what I'm meaning is find the coordinates of the point, right? So to do that, we start at the point 1, 0, start at the point 1, 0, and since 3 pi is greater than 0, we'll walk counterclockwise. Okay, so this is pi right here. This is t equals pi. Okay, then we go another pi. This is t equals 2 pi. And then we walk another pi. So we make another half loop around the circle. So the coordinates of this point would be, so the answer to this would be negative 1, 0. That would be the terminal point. All right? See how that works? Okay. All right, so let's find the terminal point for t equals pi. Okay, and I think excuse me, t equals negative pi. All right, so to find the terminal point for t equals negative pi, we start at the point 1, 0, and we'll walk clockwise negative pi radians. Clockwise pi radians, or yes, clockwise negative pi radians. Right, and so we end up at the point negative 1, 0, right there. So the terminal points for 3 pi and negative pi are the same point, negative 1, 0. All right, and then do another example. How about we find the terminal point for negative pi halves? Okay, and so let me erase this and we'll do it in red. So we start at 1, 0, and then we go clockwise pi halves radians. Clockwise pi halves radians. I believe I misspoke when I said we go clockwise negative, like for instance for t equals negative pi, we go clockwise pi radians, not negative pi radians. Clockwise pi radians. So for t equals negative pi halves, we go clockwise pi halves radians, and then we stop at the point 0, negative 1. Okay, so that would be the terminal point for t equals negative pi halves. All right, so those weren't so bad. Now, where things really get tricky is if we have to calculate terminal points for points that aren't, say, at the intercepts of the circle. See these 4 points? These are the intercepts of the circle. Well, suppose the terminal number doesn't land on an intercept of the circle. Then we have some special cases that we have to work with. So I have a chart I can show you. Let me pull it up. So bear with me. I have to. So let me get my drawing established. And this may be in your textbook. I'm not sure. And then we'll let's see here. Okay. Now, so here's a drawing on the right of the unit circle, and something that the book mentions is that the point 1, 0 basically corresponds to t equals 0. Okay, so when t equals 0, that means 0 radians. The terminal point would be 1, 0. Okay, so I should mention that. Since t can be any real number, we have to take the case for 0. Now, what's interesting is, what would be the terminal for pi over 6, which is 30 degrees, because pi radians is equal to 180 degrees, so 180 divided by 6 is 30 degrees, at least on the unit circle. Okay, so the coordinates of pi over 6 are here. So the terminal point for pi, when t equals pi over 6, right here, let's see, right here, t equals pi over 6, the coordinates of that terminal point are here, the square root of 3 over 2 and 1/2. And so I'll show you how to calculate that. Now the coordinates of the terminal point for t equals pi fourths, okay, a strange number, would be here. Square root of 2 over 2 and the square root of 2 over 2. So basically the way we would calculate the coordinates of this point, I'll clue you in, is that, okay, we need to find the x value, right, and we need to find the y value. So I'll show you how. And then right here, the coordinates of the terminal point for t equals pi thirds, which is 60 degrees. Okay, so, and it's 1/2 square root of 3 over 2, and then we have, finally in this table, okay, and it looks like it got truncated, but it's online, the coordinates of the terminal point where t is equal to pi halves, and that's 0, 1. All right, so we have this table. Now, we can extend this table and ask the question, well, what is the terminal point for, say, something like let me erase this. Okay, so you get into these kinds of issues now. We want to calculate the terminal point for t equals -5 pi over 6. Right? All right, so how would that be done? Well, we make use of the information shown in this graph right here. We know the coordinates of the terminal point of pi 6. Okay? Now, by symmetry, okay, since the circle is symmetric with respect to both the x and y axes, okay, this would be t, this point right here would be for t equals to -pi over 6. All right, -pi over 6. And can you tell me what the coordinates or the terminal point is for t equals -pi over 6? Well, we use symmetry because, okay, in this case, the x value stays the same, but the y value, since it's symmetric with respect to the x-axis, is just merely the negation of the y value. So this would be the terminal point of t equals -pi 6. Okay, and you can just see it by symmetry. Now, how about, okay, so -5 pi over 6. So that would basically equal to what? Right here, this point right here is -pi, right? If we go clockwise, and then if we, okay, so that means, well, let's see how we can work this. Oh, okay, I see now. All right, now let's draw a line parallel right here. And so can we, by symmetry, deduce the coordinates of this point? Okay, so if this is negative pi, and if we walk, okay, if we walk counterclockwise from negative pi to this point, basically this would be pi 6 radians right here. So this negative pi plus pi 6 is equal to negative 5 pi over 6. Okay, and that would be right here at this point. So if we start at the origin at t equals 0, then we go to t equals negative pi, and then we go counterclockwise pi 6, we'll come back to negative 5 pi over 6. So that's what this would be. So this arc, this arc corresponds to t equals negative pi over 6, and by symmetry, this arc corresponds to t equals pi over 6. Okay, so now we can almost get the coordinates. So we'll go here. Oops, I didn't draw that right. So like this. All right. So we can deduce that the y value stays constant here. So, and then the x value, see, y is negative. For this point, y is negative and x is negative because we're in quadrant 3. Okay, so the y value, the ordinate for this point would be negative 1/2. Okay, and in this case, by symmetry with respect to the y-axis, the coordinate, the abscissa would be negative square root of 3 over 2. And that's by symmetry with respect to the y-axis, because the circle is symmetric with respect to the y-axis. All right, so we just make use of the circle symmetry to get the coordinates of the terminal point for negative pi over 6. So it'll be negative square root of 3 over 2, comma, negative 1/2. Okay? And this is how we can visualize it by first deducing what the terminal point is for negative pi over 6 by symmetry, and then we reflect this point about the y-axis on the unit circle, and then when we reflect about the y-axis, we have to negate the abscissa, okay, and the ordinate stays the same. All right, so these are things that we'll be doing. Okay, all right, so now special kinds of terminal numbers. Now t is a terminal number, and with the terminal number, we calculate the coordinates of the terminal point. Okay, so next slide. So there's another special number, and we call it t bar. Okay, so t bar, right? And this is called the reference number. For t. And I'll show you graphically what that is. Okay, so I have an illustration to show you. Okay, so let me pull up a picture, and then I'll explain what's going on in the picture. All right. So the reference number t with a bar on top, okay, Okay, so t bar associated with the reference associated with the terminal number. Okay, so the reference number t bar associated with the terminal number t is the shortest distance along the unit circle between the terminal point determined by t and the x-axis. Okay, so simple enough. So for instance, let's look at the first illustration. So in the first illustration, the red arc is my terminal number. Okay, and so the terminal point is here. There's my terminal point. And so the shortest distance along the unit circle between the terminal point and the x-axis, okay, I have a couple of choices. I can start at t equals 0 and I can go clockwise to get to the terminal point, or I can start at the t equals 0 and go counterclockwise to get to the terminal point. So which distance would be shorter? Going clockwise to get to the terminal point from t equals 0, or going counterclockwise? Well, in this case, going counterclockwise would be the shorter distance to get to the terminal point. All right, so at least from t equals 0. So in this case, the terminal number is equal to the reference number in the first quadrant. All right, so in the first quadrant, t is equal to t bar. Now in the second quadrant, all right, in this case, I start at t equals 0, and here's the trace for my terminal number. So I want to calculate what the reference number is. Well, the reference number is the shortest distance from the x-axis to the terminal point along the unit circle. And so the shortest distance, well, from the x-axis to the terminal point, again, I can go counterclockwise. Okay, I can go counterclockwise to starting at this point to get to along the unit circle to get to the terminal point, or I can go clockwise. So in this case, going clockwise from the x-axis, okay, on the unit circle from the x-axis would give me my reference number. So the reference number is calculated starting at the point -1, 0. So I start at -1, 0 and traverse along the unit circle till I get to my terminal point, and that holds for quadrant 2. Okay, Q2. I'll call Q2 quadrant 2. Right. So clearly, the reference number. Let's see. The reference number, I believe, is always a positive number. Yeah. So we'll take the reference number to always be a positive number. Okay. So make note to self: t is always greater than 0. Okay. Now, suppose I start at t equals 0, and then I go my terminal point. I go counterclockwise, and my terminal point ends up in quadrant 3. Okay. So my reference number then would be determined by starting at the point -1, 0 and calculating the terminal number from -1, 0 to the terminal point. So this would be my reference number as shown by this red arc, right? And so this is how you would structure it for Q3. Now for quadrant 4, right? So if my terminal point after going counterclockwise around the unit circle, my terminal point ends up in quadrant 4, then my reference number, my positive reference number, would be determined by starting at 1, 0 and traversing clockwise along the unit circle until I get to my terminal point, and that holds for quadrant 4. Right, so it's the shortest distance from the x-axis to the terminal point along the unit circle. All right, so we can calculate a couple of reference numbers. So I'll give you some numbers. So in the second illustration, let's look at the second illustration here. Suppose we take t, the terminal number, to be 5 pi over 6. All right, so let's let t equal to, that's my terminal number. So my reference number, t bar, then, okay, so we have to start at -1, 0 and traverse along the circle to the terminal point. That would equal to pi 6. Okay? That would equal to pi 6. Okay. So because it would be this distance. So I'd have to go pi 6 radians to catch up to the terminal point. All right? So how about t is equal to, in this case, 7 pi over 4. What would be my reference number? All right. That would be the case. Let's see here. I don't think that case is shown here. Oh yeah, I think it's shown in the this figure right here, the fourth figure. Sorry. So in this case, for this particular figure, t is equal to, my terminal number is 7 pi over 4. All right, and so my reference number then would be this arc length distance, okay, along the unit circle. So that means reference number is equal to pi over 4. Okay, so pi over 4. Because that would be the shortest arc length distance. Remember, I go 7 pi over 4 to get to this terminal point, and then I have to go pi over 4 more to get back to the x-axis. So that residual distance to go from the terminal point back to the x-axis along the unit circle would be my reference number. It's that shortest residual number. Okay, let's see another example. Suppose I have t is equal to, so let's consider this blue arc right here. All right, so in this case, right here, so I'll say let t equal to -2 pi over 3. All right, so if that's my terminal number, then the shortest distance from this terminal number back to the x-axis would be along this arc, and that would have to be t bar. I would have to go absolute pi over 3 radians to get back to the x-axis. That would be the shortest distance along the unit circle back to the x-axis. Okay. All right. Okay. All right. So we use reference numbers. So what are reference numbers used for? Well, they're used to calculate the coordinates of a terminal point. All right. So let me pull up a slide. Let's see here. Okay, so using reference numbers to find terminal points. All right, to find the terminal point P, determined by the value of the reference number T, use the following steps. So we first find the reference number, T bar, okay, as we did in the previous example. Find the terminal point, which they often calls QAB, determined by T bar, okay. And the terminal point determined by T is, okay, so you have 4 choices, right? P plus or minus A plus or minus B, where the signs are chosen according to the quadrant in which the terminal point lies. Okay, so If you're in quadrant 3, both signs will be negative. If you're on quadrant 1, both signs would be positive. If you're in quadrant 2, the abscissa would be negative and the ordinate would be positive. And if you're in quadrant 4, the abscissa is positive and the ordinate is negative. So we'll do some examples. All right, so let's find the terminal point determined by t is equal to 5 pi over 6. Okay, so with our unit circle, okay, so since t is greater than 0, we traverse counterclockwise, and so this would be 3 pi over 6, so 5 pi over 6 is right here. So this is where this would be our terminal point. So the terminal point is in quadrant 2, okay? Because this is 6 pi over 6 right here, this is 3 pi over 6 right here, so 5 is between 3 and 6. So there's your terminal point, it's a quadrant 2. So that means that our abscissa will be negative and our ordinate is positive. And so we can use then, we know then that our reference number, okay, is the shortest distance from the x-axis to the terminal point. And that shortest distance is pi 6, right? Because in this case, in quadrant 2, the terminal number plus the reference number, their sums, at least when t is greater than 0, must equal to pi. Okay, you see how that equals to pi? Because that will put you, the addition of pi 6 to 5 pi over 6 will put you on the x-axis, where t, yes, because on the x-axis, when going counterclockwise, you'll intersect the x-axis when t is equal to pi. All right, so in this case, the reference number for 5 pi over 6 is pi 6. So now, how do we leverage this? So we know the coordinates. I think do we not do that? We had the table, right? So we go back to that table. Where was that table? Is it here? Yeah, so we go back to this table, and I've given you that the coordinates of pi 6 is the square root of 3 over 2 and 1/2. All right, so now, so so what we do is we take the point, basically, we're now at step 2. So from step 2, my q is square root of 3 over 2, 1/2, and that originates from the table. Now, and then we go to step 3, since we're in quadrant 2, the abscissa is negative. Okay, and the ordinate remains positive. Okay, so from step 3. So this information came from the table. And then this information right here for P comes from the knowledge of where the terminal point, which quadrant the terminal point is in. Okay, all right. So let's do another example. Let's say we want to calculate, all right, so let me erase this. So say we want to calculate the terminal point for t is equal to 7 pi over 4. All right, so let's let t equal to 7 pi over 4. Well, okay, so again, t is positive. So where do you think, which quadrant 7 pi over 4 is on the unit circle? Okay, so we know that this is pi halves. This is pi. Okay, this would be 3 pi over 2, which is 6 pi over 4, right? And 2 pi is 8 pi over 4. So 7 pi is halfway between 6 and 8 pi over 4. So we're going. This is in quadrant 4. This is a Q4 value, right? And so my t bar is equal to pi fourths. Remember, t bar is always a positive number because I have to add pi fourths to 7 pi over 4 to get back to the x-axis. That's the shortest distance between the terminal point determined by t and the x-axis. So it's pi fourths radians on the unit circle. Okay, that is the unit circle. All right, so now, so my q then would be the square root of 2 over 2, and these would be the coordinates of my q. So the abscissa is the square root of 2 over 2, the ordinate is the square root of 2 over 2. That's for q, and that came from the table. So now we make the adjustments for which quadrant we're in, and in this quadrant, the abscissa is positive, and the ordinate is negative. So this would be the coordinates of my terminal point. Okay. All right, so one more example. Let's calculate the coordinates of the terminal point for terminal number negative 2 pi over 3. Right? So t is equal to negative 2 pi over 3. So that means we're going clockwise now. All right, so this would be pi halves radians going clockwise, which is 3 pi over 6. Okay, so negative 2 pi over 3 is what? Negative 4 pi over 6, right? Okay, and so if we go clockwise and we stop here, this would be 3 pi over 6, negative 3 pi over 6. Right here would be my terminal number. And if I stopped here, this would be negative 6 pi over 6. Okay, so right here at the point negative 1, 0. So that means negative 4 pi over 6, which is equal to negative 2 pi over 3, is somewhere along here. We don't know exactly where, but it's going to be somewhere in quadrant 3. So this is in Q3. This is a Q3 number. Okay? All right, so now we have to find the reference number. And so the reference number would be, well, if we go another pi thirds radians from this terminal number, okay, along the unit circle, we'll reach the x-axis. Okay, so the terminal number, the reference number for negative 2 pi over 3 is pi thirds, the reference number. Okay, so now knowing that from the table, the coordinates for a reference number of pi thirds are 1/2 and the square root of 3 over 2. And since we're in quadrant 3, both the abscissa and the ordinate have to be negative. So the coordinates of my terminal point negative 2 pi over 3 are here. Negative 1/2, negative square root of 3 over 2. Okay, so that's how it works. All right. Okay, so let's do another example. So let me paste the picture in. Sorry, I'm working on the illustration. All right, so let's consider this problem. Now, suppose this is the symbol for suppose, SP. Suppose the terminal point determined by T is the point of 3/4 square root of 7/4. All right, so it's right here, as shown in this illustration. And that is on the unit circle, of course. Don't worry about this. So we know that this point is in quadrant 1 on the unit circle. Okay, and you can check. Remember, on the unit circle, you have x squared plus y squared is equal to 1. Okay, and since both of these numbers are positive, it has to be in quadrant 1. And so let's check. So x squared is 9/16, and y squared is 7/16. So yeah, so 9 plus 7 is 16. Yeah, so this is verified that it is a point on the circle. All right, so we want to find the terminal point for negative t. So all right, so what is the terminal point for negative t equal to? Now, we don't know what t is, all right, but we do know that negative t, if this green arc right here is t, then negative t is simply the reflection about the x-axis of t. All right, so all we do is by symmetry, we can see that the only thing that changes with negative t is that the y value changes sign. So for negative t, the coordinates of the terminal point would be 3/4 negative square root of 7/4 by symmetry. Okay, that's a 4 right there. Looks like a 9 or something. All right, so all we do is reflect the coordinates of t about the x-axis. All right, so now how about we consider the case 4 pi plus t. All right, so we want to find the coordinates of the terminal point determined by 4 pi plus t. So four pi plus t. All right, well in this case, here's t. You see where t is on the illustration. Now, if I start at t and I make one lap around the unit circle, I will have traversed 2 pi radians, right? And so if I make another lap around the circle, I'll have traversed another 2 pi radians, and that is if I start at t. So t plus 4 pi along the unit circle means I just make 2 laps around the unit circle, and I wind up back at t. So this is just the same as t, and so the coordinates then would be the same. Okay? Basically, I just make 2 laps around the circle and come back from the point from which I started. So the terminal point for 4 pi plus t is the same. Okay, Um, so how about pi minus t? What is the terminal? What are the coordinates of the terminal point for pi minus t? Okay, so pi minus t. So we're trying to calculate the coordinates of the terminal point for this terminal number. The terminal number is pi minus t. Okay, so we start at t, okay, and then we basically walk along the unit circle halfway around the unit circle, okay? So if we were to walk halfway around the unit circle, we wind up at this point, okay? So we have this construction right here, the blue dashed line is the construction. So we walk essentially halfway. We start at t. Oh, I'm sorry. I beg your pardon. We start at negative t. So we start at negative t, which is here. I wasn't right. I was incorrect. We start at, I beg your pardon, negative t, and then at negative t, we walk a distance equal to 1/2 the unit circle, and we end up at this point right here. Okay. So start at negative t and walk a distance equivalent to 1/2 the length of the unit circle, which is pi. So this would be pi minus t. Okay, and so we need, the challenge is to calculate the coordinates of this terminal point right here. Okay, well, we know that the coordinates of negative t, well, if we start out saying, okay, the coordinates of t are x, y, okay, which we're given, then the coordinates of negative t would be x negative y, like this, right? And by symmetry, the coordinates of this point would be negative x, negative y, okay? And then by symmetry of the square that's inscribed in the unit circle, this would be x, no, excuse me, the x value doesn't change because we stay constant, we hold x constant here, so sorry. That would be negative x y. The y sign changes, okay? So this is the formulation for pi minus t, if we know the coordinates of x, y. So all we have to do then, okay, so this implies that the terminal point would be the negative of x, which is negative 3/4, and then y stays the same. So this would be the coordinates of the terminal point for pi minus t. And all we did was we made use of symmetry. Okay, now how about t minus pi? Okay, so let's do t minus pi. Contrast pi minus t with t minus pi. So in this case, we start at t, and we walk halfway around the unit circle, or we walk pi radians. And that will cause us to end up right here at the green dot, okay? And so by symmetry then, we'll readily see that its coordinates are minus 3/4 minus the square root of 7 over 4. Right? So that would be for t minus pi. Okay. So I'm hoping you see how this works. Okay. All right. Okay. What else? Oh, okay. So another example that is in the homework section of your book, are the homework problems in your book. Let me pull that one from your text here. Right, so let's consider this illustration right here. So here, there are gradations shown on the unit circle. So for instance, right here, at this point where it says 1, this is t equals 1. Okay, so here, this would be the terminal point for t equals 1. And right here would be the terminal point for t equals 2. And right here would be the terminal point for t equals 3. Right, and then, of course, negative 1, 0 would be the terminal point for t equals pi. So it makes sense, pi being 3.14159 would be slightly further along the unit circle in the counterclockwise direction than t equals 3 is. Okay, terminal point for 4, terminal point for 5, terminal point for 6. Right, and so the question is, if t is equal to 2.5, like we did at the start of the lecture, what is its terminal point? Well, 2.5, let's see here. 1, 2, 3, that's halfway to 3, right? So this thing is divided into how many intervals? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that would be 5 units long. So 1, 2, 3, 4, 5. So this would be 2.5. So what would be your estimate for the coordinates of this point? So we can come along here, say maybe right there. We can come along here and read it from the x-axis, and the actual solution is what, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so in this case, at t equals 2.5, I get a reading of x equals negative 0.8, and y is equal to what? 1.1, 0.2, 3, 4, 5, 6.6. Okay, so 0.6. Okay, so that would be the coordinates of the terminal point. All right, so how about t equals 4.2? All right, so here's 4, and so 4.2 would be here, right here, I believe. And so we read the coordinates, and I get negative 0.6 and negative 0.9. So basically read it from the graph, the coordinates of the point on the circle. All right. Okay, so fair enough. So now what's interesting is that we can actually do some proofs of for the determining the coordinates of terminal points. So an interesting proof would be find the terminal point for pi 6. Now we know what it is from the table, but how do we know that's true? So pi 6. All right, so let me sketch a picture for you. Pull up an illustration. Okay, so P is the terminal point for terminal number pi 6, and that's shown in this illustration. And so we want to calculate the coordinates of P. That's the objective of the problem. So it's a little bit complicated, surprisingly enough. So we'll walk through the steps here. Let me grab the procedure. Sorry, the internet's slow. All right, so I'll show you how that's done. It's and I don't expect you to be able to duplicate this on the test, but it's an interesting insights. It makes use of the distance formula. So 1 second, I'm almost done here. Okay. All right. Okay, so now let's look at the illustration and keep in mind the context of the illustration. Now, so PQ, so this symbol right here with the curly line written above PQ, that stands for arc PQ. So I'll accentuate arc PQ in green. Well, actually, it's already accentuated. It's accentuated in red. So this piece of the circle right here is written in red as arc PQ. Okay, and arc PR. Okay, so arc PR is written right here, right there. Okay, they have equal arc lengths of pi thirds. So why is that the case? How do we know that they have equal arc lengths? Okay, well, we can figure it out. Okay, so we know that the arc length from here to here is pi halves. Okay, so if we call this point O, or yeah, we've already used point O, so we'll call it point S. So calling this point S, okay, the arc length from point S to point R is pi over 2 radians. Okay, and the arc length from S to P is pi 6 radians. Okay, so that means the arc length from P to R, okay, would be pi halves radians minus pi 6 radians, which is equal to 2 pi over 6 radians, which is pi thirds radians. Okay, all right, so that's how we know PR, just by doing the subtraction of lengths. All right, now for PQ, well, Q is the symmetric counterpart with respect to the x-axis of point P. So for point Q, all right, we know that this distance is pi 6, and since Q is the reflection of P about the x-axis, then this distance must also be pi 6. And then pi 6 plus pi 6 is 2 pi over 6, which is pi thirds. So that's a construction that we need for the proof of this the coordinates of point P. So we know these two arc lengths are pi thirds, so they're the same. So the next piece of the proof means that these two arcs are subtended by equal chords. Okay. So first of all, what do we mean by subtended? All right. So that's a kind of a complicated topic from geometry. What we mean by subtended is, okay, point R. Okay, so you have this line segment determined by OR right here, and then you have this other line segment determined by OP. Okay, and so we say that this arc, the arc PR, is subtended because the endpoints of the arc are also the endpoints of the two rays, or the two line segments that are determined by this angle. So this arc is subtended by these two line segments. All right. Now, and likewise, this arc right here is subtended by these two line segments, this green one and this red one. Okay, so those are for the arcs. Now, what are chords? Okay, the chords are those things on this illustration that are shown in the black dashed lines. So the chord is the line segment that connects these 2 points on the arc, right? And since the arcs are subtended by equal angles, okay, so the angle that subtends, okay, so you have this angle right here. Say we call the measure of this angle, say, theta, and then this arc is subtended by an angle of the same measure right here. So these two angles have the same measure. And because of that, then the chords which connect the 2 points which are subtended by these two angles must have the same length, right? And so that's a concept from geometry, right? So that means PQ and QR have the same length by construction. Okay. All right, so now we can calculate. Now from lecture 1, I showed you the distance formula, and we can calculate the length of PQ. All right, so using our distance formula, okay, we have P, the coordinates of P are represented as XP, YP. All right, so those are the general coordinates of XP, and this is what we want to find. We want to find XP and YP. And the coordinates of Q are represented by XQ, which equals to XP, by the way, and YQ, which is equal to the negative of YP. All right, so those are the coordinates. And then right here in this formula, we substitute in to the distance formula. Okay, so we use the distance formula. And let's see what's going on here. Okay. So the distance between P and Q is the same as this distance right here that I'm accentuating in blue. So this distance right here, all right, is right here. This would be, I'm going to try and use the book's notation, this would be the distance between, what is that? Let's see, 0, 1, yeah. The distance between P and R. Okay, but what's strange about this particular setup is that what I did was I could have written. All right, so let me show you where this, explain to you where this comes from. All right, so the distance. Let me erase this. The distance between P and R. The solution skips a number of steps, so let me fill in the details. The distance between P and R by the distance formula would equal to the square root of xp, that's xp, minus, okay, so r has, the abscissa of r is 0 squared, plus yp, and the ordinate of r is 1. All right, so we have that. Now, okay, so what I want is I want to reformulate this distance in terms of the coordinates of q. Okay, we don't have to, but if we reformulate this distance, what I've just written, in terms of q, then we'll have a very simple calculation that will result. So I anticipate ahead of time a result, achieving a result, and this would be a simple approach. Now, you could proceed solving the problem this way, but for the time being, I'm going to go ahead and replace xp with xq, since we know that they're the same. So substituting in the coordinates from point Q, or expressing this distance right here, distance PR in terms of the coordinates of point Q, we'll have this. Okay, and let's see, YQ, is that right? YQ is, I'm not sure if that's correct. Let me see. I think that may be a mistake in my notes. Yes, you're right. That is a mistake. So scratch that. Sorry. I beg your pardon. I have the wrong subscripts. So no, this is correct. This is correct. This should be XP, and this should be YP right there, not Q. So I have the subscripts wrong. I was thinking that I would reformulate it in terms of the coordinates of Q, but that's not the case. And it just so happened that I plugged in the wrong coordinates into this distance formula. All right, so this is the distance PR. So please note the corrections. Now, okay. So what do we have here? Okay. All right. So now, the next thing is, okay, see the circled equation? I'm going to simplify this circled equation in such a way. Now we know that XP and XQ are the same based on the illustration. So XP minus XQ, so let me write it up here. I'll show you how we can simplify this. So we have distance PQ is equal to, and I'll copy the equation again. That would be XP minus XQ, quantity squared, plus YP minus YQ, quantity squared. Okay. So now we know that XP and XQ are the same number. So that basically, that subtraction goes away. And so this distance between P and Q, what I'm going to do is I'm going to call it Y. I'm going to assign it a variable Y. So this would be, well, I'm sorry, I beg your pardon. I beg your pardon. I'm not reading the illustration properly. Okay, we know, let me emphasize this again. We know that this distance right here that I'm accentuating in blue, that distance is Y. Okay, so that's YP. And in purple, this distance right here is negative Y, okay, in terms of distance. So YP minus YQ would be a Y minus a minus Y, okay, which is equal to 2Y. And now remember, Y is the ordinate. Y is the ordinate of P. Okay, Y is the ordinate of the terminal number pi 6. And so the distance between P and Q then can be formulated as the square root of 2y squared, where y is the ordinate of the terminal point. And I'll use TP for terminal point. The terminal point of T is equal to pi 6. Okay, so we have that. All right, so that's where this piece right here comes from. Now, xp minus 0. Okay, so what is xp minus 0? How do we, okay, so let's work on that part now. So let me erase this. Okay, so xp minus 0. Now, xp is the, what? The abscissa of p. And so it basically means that xp is this distance right here, so it's x, right? So we can replace xp minus 0 with simply x. All right, so let me write that here. We're going to simplify this. So xp, which is the abscissa, plus yp minus 1 squared. Okay. All right, so xp is essentially x. It's essentially the abscissa of p. So that is equal to x squared. And then yp is essentially the y distance. The distance p is from y equals 0. Okay, so this would be plus y. We replace yp with y because yp is the ordinate of p, and in this illustration, yp and y are the same. Okay, so now we have the square root of 2y squared is equal to the square root of x squared plus y minus 1 quantity squared. So we have this equation. All right, and so now all we have to do is solve for one of the variables. Okay, so that's the next phase of the proof. So the hardest part was getting this equation stood up, and I apologize, I made a mistake with the subscripts here. All right, so now it's back to algebra. So we have squaring both sides. We have 2y is equal to yeah, we solve for 2y. So if we square both sides, we'll have 2y quantity squared is equal to x squared plus y minus 1 squared. And then we take the square roots again so that we can get back 2y. So 2y is equal to this expression from algebra. Then I square both sides again, okay? And I also complete the binomial square. So here's our algebraic expression. And we know that x squared plus y squared is equal to 1, so we can replace, okay, so you see this x squared right here? We replace this x squared with 1 minus y squared. Okay? And so when we replace x squared with 1 minus y squared, we'll have 1 minus y squared plus y squared minus 2y plus 1. And so when we simplify that, we'll get this. So we have 4y squared is equal to 2 minus 2y. Then we can convert this equation right here into a quadratic. So we're left with 2y squared plus y minus 1 is equal to 0. We factor, and then we get two choices for y. And of course, we reject this number because we're in quadrant 1, right? Because the ordinate of p has to be a positive number. We can't use -1. So the only choice for y would be a half. All right, so y is equal to a half. And then we just plug 1/2 into the unit circle equation. So we have x squared plus a fourth is equal to 1. And then we solve for x. And so we take the square root of 3/4, okay, because 1 minus a quarter is 3/4. And then when we do so, we have two choices, right, because of the multi-valuedness of the square root function. And so we'll reject the negative part. And so here we have the coordinates of pxy being the square root of 3 over 2 and a half. All right, so that was a rather lengthy proof. Yeah, but nevertheless very interesting. Okay, so on the website this is wrong. That's what threw me right there. Okay. Okay, so now we can say the next exercise is how about we calculate the terminal point for pi thirds. Okay. All right. Okay. All right, so to do that, I'll pull up another illustration. Okay. Let's see where do I go to get it? I'm just looking for it. So let me draw the picture first. Okay, so now consider this illustration. So what we're solving is the following. We wish to calculate the coordinates of the terminal point for t is equal to pi thirds. Okay. Now, on the illustration, I've shown a couple of things. I've shown point Q as being the terminal point for t equals pi 6. And we just calculated the coordinates of Q. Now, point P, okay, is determined by the reference number for t equals pi thirds. So in this case, the reference number, well, not the reference number, but the shortest distance between the terminal point of pi thirds and the y-axis. So that's not the terminal number. This is not the terminal number. Pi 6 is the reference number with respect to the y-axis, I guess you could say. It's the shortest distance along the unit circle from P to the y-axis. So that's pi 6. And how do we know this? Because T, the terminal number pi thirds plus pi 6 gives you pi halves, all right? So P and Q are drawn thusly. Now, it turns out this yellow line, the equation of this yellow line is y equals x, okay? And so y equals x, and it basically bisects the arc connecting Q and P. So line y equals x is a bisector for arc P and Q. So P, we can say that P is the reflection of Q about the line y equals x. So let me write that down for you. Okay, so in this figure, P is the reflection of Q about the line y equals x, all right? And so what do we know about coordinates reflected about the line y equals x? Well, let me take an aside and show you what the utility of knowing that is. All right, so if I sketch the line y equals x right here, okay, so this is y equals x. And I have, here's P, okay, and if I were to reflect P about the line y equals x like this, so a reflection, and I'll call it P prime, okay, so P and P prime are reflections about the line y equals x. What it means is the following. If the coordinates of P are x, y, then a reflection about the line y equals x, okay, the reflected point, the coordinates of the reflected point about the line y equals x, you just reverse the coordinates like this, okay? So this is what a reflection about the line y equals x yields. If you were to reflect a point about the line y equals x, you reverse the coordinates. You interchange the abscissa and the ordinate. Okay, so now, how does that help us with this calculation? Well, P is the reflection of point Q about the line y equals x. Okay, based on the way, based on the symmetry of the circle and the symmetry of the line y equals x. Okay, so we know that Q is what? Okay, we know the coordinates of Q are the square root of 3 over 2 for the abscissa and 1/2. Okay, so since P is the reflection of Q, then the coordinates of P, you just interchange the abscissa and ordinate. Okay, so you have that. Okay, and so that's your terminal point for T equals 2 pi thirds. Okay, all right, so it's a little bit tricky to know that. So that's how it all fits together. Okay, all right, so I think this roughly completes the lecture material for the first section of Chapter 2 in your book. So I'm going to go ahead and in this particular video and post it on the website. So we'll call this lecture topic 2.1. All right, so